Modern warfare begins long before the first explosion. It begins with calculation. Every missile represents a solution to a strategic problem. Range, accuracy, and timing define effectiveness more than sheer firepower. In this analysis, we examine two very different missile philosophies. Kh-101 prioritizes endurance, stealth, and long-range precision. ATACMS focuses on speed, responsiveness, and tactical immediacy. Both operate under strict physical and mathematical constraints. Fuel efficiency, guidance accuracy, and trajectory shape their roles. These weapons are designed to compress time and space on the battlefield. Understanding how they work explains why they are used. These weapons are deterministic machines. Given identical inputs, they will always behave in the same way. What changes is the environment, terrain, air defenses, electronic interference. Design determines how well a missile adapts. Modern targeting maps are not geographic representations. They are layered data models combining elevation, radar coverage, and probability fields. Distance is no longer a simple measurement in kilometers. It is calculated in exposure time and reaction windows. Altitude is chosen not for efficiency, but for survivability. Every meter higher or lower changes detection probability. Speed, often assumed to be decisive, is only one variable in a much larger equation. Faster does not always mean safer. Missiles are designed around trade-offs. Engineers cannot maximize range, speed, stealth, and payload simultaneously. Instead, each system optimizes for a specific mission profile. Everything else becomes a compromise. One philosophy avoids defenses by staying invisible. The other overwhelms defenses by denying them time. These two approaches define modern long-range strike doctrine. Both are effective under different conditions. The Kh-101 cruise missile embodies the concept of persistence. It is designed to survive long enough to reach deeply defended targets. Rather than brute force, Kh-101 relies on reduced radar cross-section and low-altitude flight. Detection is delayed, not challenged. Structurally, the missile resembles a compact unmanned aircraft. Lift, efficiency, and stability dominate its design. This architecture allows sustained flight at subsonic speeds. Endurance replaces acceleration as the primary advantage. At the core of this concept is a small turbofan engine. Unlike rockets, it consumes oxygen from the atmosphere. This dramatically increases fuel efficiency. Thrust is lower, but burn time extends from seconds to hours. With this design, the Kh-101 achieves ranges exceeding 2,000 kilometers under optimal conditions. Range becomes strategic depth. Internal volume is dominated by fuel storage. Every kilogram of fuel translates directly into extended reach. The missile's operational value lies in its ability to approach targets indirectly. It can navigate around defended zones rather than through them. This concludes the strategic foundation. Next, we dissect the Kh-101 inches full technical detail, component by component. The Kh-101's turbofan engine operates on a fundamentally different energy model than rocket propulsion. By ingesting atmospheric oxygen, it converts chemical energy into sustained thrust with far greater efficiency. This engine produces relatively low thrust, but thrust is applied continuously. Over time, this results in greater total impulse than short-duration rocket burns. From an engineering perspective, the missile trades acceleration for endurance. Its mission profile assumes time is available, but survivability is essential. Air intake geometry is carefully shaped to reduce radar reflections. Even minor angles are optimized to scatter electromagnetic waves away from threat radars. Before reaching the compressor, airflow is stabilized to reduce turbulence. This improves combustion efficiency and engine lifespan. Thermal output is another critical variable. Lower exhaust temperatures reduce infrared signature, complicating IR-based interception systems. At cruise speed, the Kh-101 typically operates well below the speed of sound. This avoids shockwave formation and acoustic detectability. Subsonic flight also simplifies control algorithms. Stability margins are wider, allowing more precise navigation corrections. Fuel flow is continuously regulated based on altitude, speed, and temperature. The missile behaves more like an aircraft than a projectile. This design allows the Kh-101 to remain airborne for several hours if required. Time becomes a tactical resource. Guidance begins with an inertial navigation system, or INS. Gyroscopes and accelerometers track position without external input. However, inertial systems drift over long distances. Without correction, errors accumulate exponentially. To counter this, satellite navigation updates are periodically integrated. These corrections reset accumulated positional error. In contested environments, satellite signals may be degraded. The Kh-101 compensates using terrain reference navigation. Terrain contour matching compares radar altimeter data to preloaded digital elevation maps. This process anchors the missile to physical geography. At low altitude, even small terrain features become navigational references. Hills, valleys, and ridgelines guide flight. Typical cruising altitude ranges between 30 and 70 meters above ground level. This places the missile below many radar horizons. Radar detection probability decreases sharply at these altitudes due to ground clutter. Signal discrimination becomes difficult. Flight control surfaces respond continuously to micro-adjustments. Dozens of corrections occur every second. Each correction is mathematically minor, but collectively they maintain precise trajectory control. The missile's path is rarely direct. Instead, it follows a pre-planned route, optimized to avoid defended sectors. This route planning resembles graph optimization problems used in computer science. Threat zones are treated as weighted obstacles. The objective is not shortest distance, but lowest cumulative risk. Time is exchanged for survivability. Warhead mass is moderate compared to ballistic systems. Precision compensates for explosive yield. With meter-level accuracy, structural targets can be disabled rather than obliterated. Functional damage replaces area destruction. This makes the Kh-101 effective against infrastructure targets. Power grids, command centers, and logistics hubs are prioritized. The missile's effectiveness is measured in system disruption. Its impact persists long after detonation. Unlike tactical missiles, Kh-101 is rarely used for immediate battlefield effects. Its role is strategic pressure. Survivability throughout the flight is the defining metric. Detection delay directly correlates with mission success. In essence, the Kh-101 is a weapon of patience. It wins not by force, but by persistence. This design philosophy reflects a long-standing emphasis on deep strike capability. Strategic reach outweighs immediacy. Every subsystem supports this objective. Efficiency, concealment, and autonomy are prioritized. The missile's slow approach is intentional. It allows defenses to become saturated or distracted. In large-scale strikes, multiple Kh-101 seconds may arrive from different vectors. This complicates interception planning. Time-on-target coordination becomes a strategic tool. Simultaneous arrival maximizes disruption. This coordination relies on predictable flight behavior. Determinism ensures synchronization. Unlike ballistic systems, last-second evasive maneuvers are limited. Planning replaces improvisation. The Kh-101 is not designed to react, it is designed to endure. Its success depends on preparation, intelligence, and accurate mapping. Having fully dissected the Kh-101, we now turn to a missile built on the opposite principle: speed over stealth. ATACMS approaches the strike problem from a fundamentally different perspective. It assumes detection is inevitable and focuses instead on minimizing reaction time. At the core of ATACMS is a solid-fuel rocket motor. This choice prioritizes simplicity, reliability, and instantaneous thrust. Solid propellant combines fuel and oxidizer into a single mass. Once ignited, combustion proceeds at a predetermined rate. Unlike turbofan engines, solid rocket motors cannot be throttled. Thrust is binary, on or off. Upon ignition, ATACMS reaches peak thrust within milliseconds. Acceleration forces rapidly exceed multiple G. This explosive acceleration defines the missile's operational logic. Speed compresses the entire engagement timeline. The missile exits the launcher already committed to its trajectory. There is no loiter, no diversion. Within seconds, ATACMS climb steeply into thinner air. Reduced drag allows velocity to be preserved. Altitude is not chosen for concealment, but for ballistic efficiency. The missile trades visibility for speed. Once motor burnout occurs, the missile transitions into ballistic flight. Gravity becomes the dominant force. This phase follows a predictable parabolic arc governed by initial velocity and launch angle. From a physics standpoint, the missile now behaves like a projectile. Its path can be calculated with high accuracy. Guidance during ascent relies on inertial navigation, supported by GPS correction. Errors are minimized early. Unlike cruise missiles, ATACMS performs few mid-course adjustments. Stability is preferred over maneuvering. This reduces control complexity and improves reliability under electronic warfare conditions. The terminal phase begins as the missile re-enters denser atmosphere. Velocity remains extremely high. Impact speeds are often measured in Mach numbers rather than meters per second. At these speeds, interception windows shrink to mere seconds. Defensive systems must react almost instantly. Even when detected early, prediction accuracy becomes a challenge. Small timing errors lead to large missed distances. ATACMS exploits this by denying defenders sufficient time to form firing solutions. Its survivability is derived from kinematics, not stealth. Speed replaces invisibility. Warhead configurations are optimized for tactical effect. Fragmentation and blast are tightly controlled. High impact velocity significantly increases effective lethality. Kinetic energy supplements, explosive force. Targets are typically time-sensitive. Ammunition depots, airfields, and troop concentrations are prioritized. The goal is immediate disruption rather than prolonged degradation. Launch platforms such as HIMARS enhance operational flexibility. Mobility reduces vulnerability. Shoot and scoot tactics shorten exposure to counter battery fire. From a command perspective, ATACMS compresses the kill chain dramatically. Decision to impact time is minimized. This compression limits adversary response options. Detection does not guarantee interception. Ballistic flight leaves little room for improvisation on either side. Once launched, the outcome becomes a statistical problem rather than a tactical one. Probability of interception depends on sensor coverage, interceptor readiness, and timing accuracy. Even advanced air defense systems face diminishing returns against high-speed ballistic targets. ATACMS is therefore best understood as a weapon of inevitability. It overwhelms by denying time. Its limitations are equally clear. Range is shorter than that of cruise missiles. Flexibility during flight is minimal. The missile cannot adapt to unexpected changes. This makes intelligence accuracy before launch critical. Errors cannot be corrected later. ATACMS rewards decisive command structures. Hesitation reduces its advantage. Where Kh-101 stretches pressure over hours, ATACMS delivers it in minutes. With both systems analyzed individually, we can now compare how these opposing philosophies shape modern warfare. Placed side by side, Kh-101 and ATACMS reveal fundamentally different optimization targets. One minimizes detection probability over time. The other minimizes reaction time after detection. From a systems perspective, Kh-101 treats air defenses as obstacles to be avoided. ATACMS treats them as clocks to be outrun. Kh-101's subsonic speed increases exposure duration but reduces observability. ATACMS accepts full observability in exchange for extreme kinematic advantage. If interception probability is expressed as a function of detection time and interceptor readiness, the two missiles invert the equation. One stretches the denominator, the other collapses the numerator. Cruise missiles rely on cumulative survivability. Ballistic missiles rely on compressed engagement windows. In practical terms, Kh-101 forces defenders to maintain long-duration vigilance. ATACMS punishes even momentary delays. Time-on-target coordination illustrates this contrast clearly. Kh-101 synchronizes arrivals through precise scheduling over hours of flight. ATACMS synchronizes through launch timing alone. Seconds replace hours as the dominant variable. From a mathematical standpoint, Kh-101 reduces risk by path optimization. ATACMS reduces risk by velocity magnitude. Fuel efficiency versus thrust density defines their propulsion trade-off. One maximizes total impulse, the other maximizes instantaneous impulse. Guidance philosophy also diverges sharply. Kh-101 continuously updates its solution based on terrain and navigation inputs. ATACMS relies on pre-computed trajectories with limited correction. Predictability enables reliability. In electronic warfare environments, these differences become critical. Satellite denial affects cruise and ballistic systems differently. Kh-101 mitigates signal loss through terrain-referenced navigation. ATACMS mitigates it by shortening exposure time. Target selection reflects doctrinal intent. Kh-101 favors infrastructure nodes, whose disruption cascades through systems. ATACMS favors time-sensitive tactical assets, where delay nullifies value. Strategically, Kh-101 applies sustained pressure. Its impact accumulates over days or weeks. ATACMS applies shock. Its value is immediate and localized. Neither approach is universally superior. Effectiveness depends entirely on operational context. Against layered air defenses, low-altitude cruise missiles exploit radar limitations. Against dispersed targets, ballistic speed dominates. Resource allocation also differs. Cruise missiles demand extensive planning and intelligence preparation. Ballistic missiles demand rapid decision-making and accurate real-time targeting. From a logistical standpoint, launch platforms shape usage. Air-launched systems extend strategic reach. Ground-launched systems emphasize responsiveness and survivability through mobility. Doctrine determines how these systems are integrated. Missiles do not operate in isolation. They are nodes within larger command, control, and intelligence networks. Success depends on sensor fusion, communications resilience, and timing discipline. A precise missile with poor intelligence is ineffective. A fast missile with delayed authorization loses relevance. Modern warfare rewards synchronization across domains. Air, land, space, and cyber inputs converge. Kh-101 exemplifies long-cycle strategic operations. ATACMS exemplifies short-cycle tactical execution. Together, they illustrate how strike capability has diversified rather than converged. Instead of a single optimal weapon, modern forces deploy complementary systems. One shapes the battle space. The other exploits moments within it. This duality defines escalation management. Pressure can be modulated in time or intensity. Engineering choices thus become strategic levers. Hardware encodes doctrine, yet beneath doctrine lies physics. Equations constrain every decision. No missile escapes trade-offs imposed by mass, energy, and time. Technology refines options, but does not eliminate limits. Understanding these limits is what separates analysis from assumption. With comparison complete, we now step back to examine what these systems mean for the future of warfare. When the technical analysis ends, what remains is implication. Weapons do not exist in isolation. They reshape how decisions are made. Kh-101 and ATACMS are not merely tools of destruction. They are embodiments of how modern militaries think about time, space, and control. One stretches pressure across geography in hours. The other compresses it into minutes and coordinates. Together, they demonstrate that modern conflict is no longer linear. It is layered, asynchronous, and algorithmically managed. Precision has replaced volume as the dominant measure of effectiveness. Fewer weapons now achieve greater systemic impact. This shift fundamentally alters escalation dynamics. Power is applied selectively rather than indiscriminately. Modern missiles transform distance from a barrier into a variable. No depth is inherently safe. They also transform time. Reaction windows shrink, and hesitation becomes costly. In this environment, command structures must evolve. Decision speed becomes as important as decision quality. Yet faster decisions carry greater risk. Compression amplifies the consequences of error. Algorithms assist targeting, navigation, and timing, but they do not assign value to outcomes. A missile does not understand context. It understands parameters. Ethics, therefore, cannot be automated. Responsibility remains human. Engineers design systems to obey physics. Commanders decide how those systems are used. The missile executes flawlessly, regardless of intent. Precision does not imply judgment. As weapons become more reliable, accountability becomes more critical. Technology removes friction from warfare. It does not remove consequence. Every improvement in accuracy increases the weight of decision-making. Kh-101 shows how persistence can quietly reshape a battle space. ATACMS shows how speed can abruptly redefine it. Neither guarantees victory. Both demand integration into broader strategy. Wars are not won by missiles alone. They are shaped by how force is timed, targeted, and restrained. The future battlefield will not be louder. It will be faster, more precise, and less forgiving. Systems will calculate trajectories. Humans must calculate consequences. As detection improves, concealment evolves. As speed increases, reaction diminishes. This cycle has no natural endpoint. Only deliberate limits can slow it. Weapons will continue to advance. Physics allows it. Doctrine will continue to adapt. Strategy demands it. But restraint must be chosen. It cannot be engineered. In the end, missiles reflect the societies that build and employ them. How they are used, not how they work, will define the future of warfare.